All right, I want you to think of your Cambridge Physics 0625 exam not as some long, slow marathon, but as a high-speed Formula One race. And right now, you are pulling into the pit stop. Welcome to this explainer. Time is ticking, the pressure is totally on, and frankly, you can't afford a single loose bolt. So today, we're focusing on maximum precision with absolutely zero fluff to get your space physics revision totally dialed in. We are locking in on stars, galaxies, redshift, the Big Bang, and Hubble's law. There's no generic study advice here today, just the high-stakes strategy you actually need to secure your grade. Let's get into it. First things first, I've got a question for you, and I want you to lock in an answer right now in your head. When a low-mass red giant has consumed most of the helium in its core, what does it turn into? Is it A, a yellow dwarf, B, a white dwarf, C, a supernova, or D, a neutron star? Seriously, commit to an answer. Okay. If you guessed anything other than B, a white dwarf, well, you've just hit a pretty major roadblock. Guessing wrong on a foundational question like this represents a painful mistake that literally costs you easy exam marks before you even get to the complex calculations. We have got to eliminate these unforced errors.
So let's jump right into Section 1, the exam speed trap.
You know, under strict exam timing pressure, ordinary revision just fails. Simply skimming a textbook isn't going to cut it when you're facing precise traps that are basically designed to catch you out and sink perfectly good grades. I'm talking about those classic frustrating mistakes: missing units on your final answer, rounding your numbers way too early in a multi-step calculation, giving these vague, unscientific explanations, mixing up your graph axes, or, suggesting really weak improvements for practical investigations. You might actually know the physics perfectly, but if you fall into these mechanical traps, your marks are going to plummet.
But don't worry, because in just a minute, I'm going to reveal a specific examiner clue. It's a powerful four-step framework that will completely change how you structure your written answers. It is literally the key to unlocking those top-band method marks. But before you can use that framework effectively, you absolutely have to understand the underlying physics of the extremes of our universe. Which brings us to Section 2, Massive Star Life Cycles.
Let's shift gears for a second into the high-stakes physics of massive stars. This is where the life cycle gets significantly more extreme. We aren't talking about low-mass stars like our sun anymore. We're talking about absolute giants. When a massive star finally runs out of fuel, nuclear fusion stops, and the star releases its energy in a completely colossal event. Think about the Crab Nebula, for example, the glowing remains of a supernova explosion that was actually observed by Chinese astronomers way back in 1054. In a supernova, the temperature spikes so incredibly high that nuclei fuse into elements heavier than iron. This massive explosion throws all that material, all those heavy elements, out into space to form a nebula. And this is crucial, because this scattered material literally becomes the building blocks for brand new stars and their planetary systems.
Now, after that massive explosion, the core of the star collapses, and it goes down one of two very extreme paths. You really need to be able to contrast these two remnants. First, you might get a neutron star. This is a crazy, dense core that spins incredibly rapidly, acting as a pulsar and sending out regular pulses of radio waves. But if the original red giant was exceptionally massive, you get the second outcome, a black hole. This remnant has such an unimaginably large density that its gravitational field stops absolutely anything from escaping its surface, not even light.
To really wrap your head around just how dense a black hole is, think about a volume of exactly 1 cubic centimeter. Just picture the size of a standard six-sided die. In a black hole, matter is packed so densely that the entire mass of the Earth, the whole planet, would fit into just that tiny dice-sized volume. It's mind-blowing. And because not even radiation can escape, we can't actually see them directly. We only know they're there because of the intense X-ray radiation that gets emitted when nearby material, like gas from a neighboring star, is violently pulled in.
Okay, let's move on to Section 3, Redshift and Expansion.
Shifting our focus from the life cycle of individual stars to the scale of the entire universe, there is a definition you absolutely must have locked and loaded: redshift. Redshift means that light emitted from stars in distant galaxies appears shifted toward the red end of the spectrum. Why does this matter for your exam? Because it is the primary evidence that the universe is expanding, which directly supports the Big Bang theory. If a question asks you for evidence of the Big Bang, redshift is the foundational concept examiners are actively hunting for. And beyond just redshift, your exam radar needs to be tracking a few other essential concepts. You've got to know that the universe is made up of billions of galaxies, and our Milky Way is just one of them. You also need to be able to describe and explain cosmic microwave background radiation, or CMBR. And practically speaking, you need to be ready to use the Hubble constant in various equations. You'll use it to calculate the speed at which a galaxy is moving away from us, its distance, and you might even use it to estimate the actual age of the universe itself.
That takes us to Section 4, Top Band Exam Answers.
Now, knowing all these facts is really only half the battle. Knowing how to write them down exactly how the Cambridge mark scheme demands, that is what secures the grade. Remember that ultimate examiner framework I teased earlier? Well, here it is. This 4-step sequence is your absolute secret weapon for explanation questions. Step 1, state the core concept. Step 2, provide the evidence or data. Step 3, connect them with clear scientific reasoning. And Step 4, wrap the whole thing up using precise examiner wording and terminology. This is the exact blueprint required to unlock top band method marks and, frankly, leave the examiner with no choice but to give you full credit.
Let's actually spot the difference in action here. Imagine a flawed student answer that just says, the universe is bigger because light is red. I mean, it's incredibly vague and totally lacks proper terminology. That's getting 0 marks. Now compare that to a top band response. Light from distant galaxies is redshifted, evidencing the universe's expansion and supporting the Big Bang theory. See the difference? It perfectly hits the concept, provides the evidence, uses the mandatory scientific reasoning, and totally nails the terminology. It's a textbook application of the framework.
So you now have the space physics framework and the knowledge of stars, galaxies, and redshift to ace this section. But there is still an unresolved problem. You are still completely vulnerable to the brutal calculation, graph axis, and practical data traps hiding in the rest of your Physics 0625 paper. If you don't know how to navigate the common traps by question type, all this great space physics knowledge we just went over won't save your overall grade. You know how stars die, you know how the universe expands, and exactly how to prove it to the examiner. But as you look up at the night sky, I want you to ask yourself, if the universe is constantly accelerating outwards, what exactly is it expanding into? Keep questioning that and keep practicing. To ensure your grade is completely secured and you actually survive the rest of the paper's traps, make sure you subscribe to our YouTube channel Ace the Exams at Ace the Exams IGCSE to excel in your Cambridge examinations. Your mandatory next step is to dive into our last 7 days revision map explainer to completely bulletproof the rest of your paper. Don't leave your grade to chance. Let's finish this race strong.